Okay. Thanks a lot. So my goal today is to lead you to one of the entrance door of infinity. So there's a video that should start there. You can follow me on a starry night and look at a specific direction in the sky, to the center of our galaxy, the Milky Way. This is a region full of turbulence and dust and cloud. What do you expect to find there? Stop the video, please, and we will see later what we can find there. You need to understand what a black hole is. So you can think to an enormous concentration of matter in a relatively tiny area. It is a space where the force of gravity is so strong that nothing, included light, can escape from that. In 1916, what today we call a black hole was just a solution of a tensorial equation written by this guy, something handwritten on paper. Of course, you don't need to understand all this math in order to grab two basic things. One, nothing can go faster than the speed of light. And two, everything, including light, are attracted by gravity. Now, difficult question. How fast you should go around the Earth if you don't want to fall on it? At some point you will learn energy conservation, and we'll learn how to derive this formula that tells you that this velocity should be 11 kilometers per second. But now, what if you squeeze the mass of the Earth close to the size of a football balloon? This escape velocity will increase to 90,000 kilometers per second. And what if you squeeze the mass of the Earth to the size of a grape, 1 centimeter? The mass stays the same, the radius is 1 centimeter. What happens? The escape velocity becomes faster than the speed of light. But nothing can go faster than light. So the conclusion is nothing, not even radiation, can escape from the Earth. Our planet will become invisible. Our planet will become a black hole. The Schwarzschild radius, do you know how to pronounce Schwarzschild? The radius is the distance at which the escape velocity exceeds the speed of light. What is this distance? We saw for the Earth is 1 centimeter, the size of a grape. For a more massive objects like the Sun, it's much larger, it's 3 kilometers. And it's proportional. You see from this formula, if you have an object, a star, for instance, 10 times the mass of the Sun, this radius is 30 kilometers. You see from the formula. Now, it's not that interesting if the radius is inside the objects. But for very compact objects, the Schwarzschild radius lies outside, so light cannot escape. It will become a black hole. A star can become a black hole. How a star can become a black hole? Well, you know that inside a star, there's... a star can become a black hole by collapsing, but before this video, I want to explain something with this slide. Thanks. What's inside a star? There's the gravity compression, and there's the radiation pressure that balances it from the burning fuel. You see all the burning fuels there. Now, what happens when the star runs out of burning fuel? The gravity compresses the star. All these bands disappear. Okay, like that, yeah. All this band disappears, and a new core is formed if a star is small enough. If the star is large enough, larger than 2-3 solar masses, the gravity of the core is too big to support itself. It continues to implode. The Schwarzschild radius goes outside, a black hole is formed. The mass of the black hole is concentrated in a region that is called the singularity. Here is where we approach to infinity. Why? Because we have almost infinite density. The space-time is is infinitely curved, and we believe that the laws of physics do not hold there. What we call the event horizon is the surface of a sphere having the Schwarzschild, the radius. Things can fall from the event horizon into the black hole, but nothing can go out of it. We call this this way because an event occurring at this boundary, we don't have information from it, so we cannot tell if it happened or not. You may wonder, what happens to matter disgregating in the black hole? You see, it is up and glow and emit lights, X-rays, radio waves, powerful gamma rays, and it's formed what is called the accretion disk that is million degrees hot. And what happens if you have a charged particle rotating around? They create magnetic field. Matter turns around the field line and form these very energetic jets that are ejected by the black hole close to the speed of light. Now, you know what a black hole is, how a black hole is made. You may wonder, how can we find a black hole in the sky? Well, you know how big is the effect of matter around, so you can look for binary objects, objects where you have two stars dancing one around the other, when one of the partners is invisible. Is it enough to tell that it is a black hole? Well, we need something else. We need a stronger radiation from its core. Well, in 1971, we discovered a powerful X-ray star that was invisible from a constellation called Sinus X1 that was emitting X-rays. It was as big as 20 solar masses. It was too big for being a neutron star. It was the first black hole ever discovered. You see in this artist's view how the black hole eats matter from its companion. We know in the similar way that there are black holes at the center of spiral galaxy. This is M106, but they can have a mass as millions of solar masses. They cannot be created by the collapse of a large star. We don't know how they have been created, probably by merging together big black holes and other things where the object was when the universe was very young. And there's another way to infer the existence of a black hole from the movement of stars. You see, the position of the stars have been recorded along the years. You see, they are rotating around a common center. This is close to the center of our galaxy. It's called Sagittarius A. Kepler's law tells that something should be there. And they also teach us how to calculate the mass. The mass of this object has been calculated to be 3 millions of solar masses. What do you think is there? Now, you understood, okay, you can stop the video. You understood how to infer the existence of a black hole from the radiation, from anomaly in the light or in the movement. But we want something more. We want to have a picture of a black hole, an image of the accretion disk of the relativistic jets. This is the goal of the Event Horizon Telescope collaboration. It's a global network of radio telescopes. They managed to put together a worldwide network of telescopes that are able to detect radio waves from the deep space behind a curtain of dust and clouds. If they put all these radio telescopes to work together, they will obtain a resolution that is so tiny. It's just like you were able to read a newspaper from your chair. If I put a newspaper on the moon, so tiny. Or just like if you are able to see a human hair in Paris, if you look from New York. This is the resolution they obtained, and with this resolution, we can look, video should start, yes, we can look at the Virgo cluster, where we know there's a big galaxy called M87. There's a lot of activity there. There are jets, thousands of light years long. In 1994, the Hubble Space Telescope measured the mass of this object. It was as large as 7 billions of solar masses. In a space that is slightly larger than our solar system, a lot of materials whirl around at 1,000 kilometers per second, and on the 19 April 2022, we had the first image of the black hole. You see there? No? Yeah, okay, yeah. Okay, no, that's okay. The first image of a black hole is this one. What does it remind? To me, it reminds, what? Yeah, a donut. So what you see there is sugar. No, sorry. What you see there is the accretion disk. Accretion disk, you know, is the last stable orbit. Everything that is close to that goes inside, and you see. Why is this way? It's brighter from one side, because the brighter side is the one that is closer to you. The darker side is the sector that goes apart from you. Look at this image. Think that it takes 350 terabytes per day to be produced, 6 meters cube, 6 cubic meter of hard disk. And also think that rays from this image has traveled millions of years. This object is 52 millions of light years distance. They traveled millions of years just to reach our telescopes. Yes, infinity can be in a donut. Now, can we produce a similar images for the center of our galaxy? The center of our galaxy is closer, of course, but it's much, much smaller. It's just as small as the orbit of Mercury, and it's full of dust and clouds, and it's continuously moving. So you need an even better resolution, just like if you're able to see the donut. You see the donut? If I put the donut on the moon, this is the resolution you need. And once you have all the images from, this is not a real image. This is what we expect from simulation. We used to do simulation before observing real things. Yes, you see all the rays there are distorted by gravity. The lighter part is the part approaching to us. This effect has a name, Doppler beaming effect. And also we have a simulation for the gas falling into the black hole and emitting radio waves. Okay, there's a radio waves emitted there. So after many years of 3 years of data, they put the images together. Now, putting the images together is not the end of the job, because they have to find the better way to put them together, to fill the gaps. Among this image, what do you think is the best one? This one is the best. So, don't lose the best part. After all of this work, on the 12th of May 2022, the humankind had the first image for the center of our galaxy. Yes, another donut, much smaller. We can see how smaller it is. This is the first donut, M87, as large as the solar system's Y. If you go there, this is the center of our galaxy, Sagittarius A. So we found that Einstein was right. Relativity, as he expected to work, worked there. So can you imagine something handwritten more than 100 years ago from a guy describing a very extreme environment was correct? Einstein was right. Back on the Earth now, from science to humans, because science is made by human, with a final message for you that is multiple. First of all, this is an example of a guy that was creative in the sense that nobody before him thought to gravity as a consequence of geometry. And geometry can be so distorted that light can fall inside. Then, if you prove to something to be correct, be stubborn and persevering in insisting in your idea. Stephen Hawking is someone that proposed that a particle radiation can go outside from event horizon. It was ridiculed at the time, but eventually we found that he was right. And finally, do not stop to be curious. The job of Katie Bowman was eating donuts. No, sorry, I'm joking. Was to develop an algorithm for reconstruction from the Event Horizon telescopes. You see from what she obtained, you see from her face how curiosity can pay off. Thanks a lot.
Leonardo's talk about black holes was truly captivating. The idea that something so dense and powerful exists in our universe can be fascinating but humbling. Sadly, that brings us to the end of this session. Thank you to our speakers, Mrs. Hotsworth and Mr.